In this lecture, we'll talk about Copenhagen interpretation of quantum mechanics. Copenhagen is the capital of Denmark, and the early quantum mechanists like Niels Bohr, Werner Heisenberg, uh, these guys sort of sat together and outlined the basic guidelines or basic principles which described how quantum mechanics works, or the basic principles of quantum mechanics. And they were six in number, starting with the first one, which said that a system is completely described by a wave function psi representing the state of the system, which evolves smoothly in time except when a measurement is made, at which point it instantaneously collapses to an eigenstate of the observable measure. So in the last class we talked about quantization, and plus quantum mechanics is given a probabilistic nature, and these two together take care of the uncertainty principle. Which is also sort of related with the wave nature of quantum systems. So these are sort of corresponding to each other. Okay, now this psi or psi is called the wave function of the system, which tells about the state of the system. Now, according to Max Born, psi square this is related to the probability of the system to be found at certain state. Now they may look not so very clear right now, these definitions, but it will make sense as we'll proceed. But the basic idea is that the uncertainty principle is being taken care by the introduction of quantization and by giving a probabilistic treatment to providing a probabilistic nature to quantum mechanics. And this is done by describing the state of a system using a wave function which is called psi. And the probability of the system to be in a certain state is given as the modulus square of this wave function, and this definition was given by Max Born. The second point was that the description of the nature is essentially probabilistic, with the probability of a given outcome of a measurement given by the square of the modulus of the amplitude of the wave function. So I sort of included this in the first case, but actually the second point says that the square of the modulus of the wave function is the probability of an outcome, which is same as saying the probability of a system to be found in certain state. And this was because of Max Born, and this is also called the Born rule. Third point, it is not possible to know the value of all the properties of the system at the same time. Those properties that are not known exactly must be described by probabilities. And this is called Heisenberg uncertainty principle. This is the third point. We'll cover this. We have glanced over this, but we'll cover this in one of the lectures to cover in detail principle. And this is all due to the way it has been expressed. So, to give some credit to nature, this whole construct has been developed. Fourth one. Matter exhibits a wave-particle duality. An experiment can show the particle-like properties of matter or the wave-like properties. In some experiments, both of these complementary viewpoints must be invoked to explain the results, according to the complementarity principle of Niels Bohr. Okay, so the third point is the complementarity principle of Niels Bohr. So according to the relevance, a system can give us information in terms of classical mechanics when we talk about the aggregate of the system, or if we are interested, it can also give us information in the intricate information in terms of quantum mechanics. So as a sum, as a whole, the system can be treated as partly as quantum mechanics or as a classical mechanical, to really understand the working of the system, how this whole system is working. We also have seen things like correspondence principle, where when a quantum number goes to a very large number, then it behaves like a classical system, things like that. So there's a whole lot of things that can be considered when we try to understand the nature of a system. Point fifth. Measuring devices are essentially classical devices and measuring only classical properties such as position and momentum. So the measuring devices, basically what they do is that they try to figure out that in which system, in which state the system is. Now we said that the sigma square or psi square is the probability of finding a system. And when we measure, what we do, we actually for sure we know that what is the state of the system. For example, we do not know the position of a particle, and it expressed as a wave function, the probability of as a probability. But we can do a measurement and find precisely what is the position of the particle. Or let's say other example, the example of that harmonic oscillator. We may not know the energy of the harmonic oscillator, but if we do a measurement, we can actually try to find out in which state the harmonic oscillator is. It can be in E0 state, it can be in E1 state, it can be in E2 state, and this is the process of measurement. And this is what these classical systems do. And this whole process is also called, in terms of quantum mechanics, is called wave function collapse. So this is the probabilistic nature, and here you see we have not really violated uncertainty principle. Here we had some uncertainty principle being followed. Here we have measured the energy of the system, but we actually have lost a whole lot of information when we did this measurement. So uncertainty principle is not violated in all this process. So the overall idea is to express the system as a probability function, the state of the system as a probability function, and then when we do a measurement, this happens. So all this while the uncertainty principle is not violated. What is the sixth point? The sixth point is the quantum mechanical description of large systems will closely approximate the classical description, which we already have talked about. This is called the correspondence principle. Just to read again, the quantum mechanical description of large systems will by large system means for large quantum numbers, will closely approximate the classical description. Now these 6 points were discussed in Copenhagen Interpretation. Many people were not happy with this. Einstein especially was not happy with these kinds of description of quantum mechanics, because he sort of believed that inherently the everything is deterministic and not probabilistic, and he wrote a paper, something called very famously known as Epr Paradox, where he sort of contradicted or sort of gave loopholes in some of these postulates or principles. And we'll probably talk about all this in different classes, but these 6 points are called Copenhagen Interpretation. And from next class onward, we'll try to be more quantitative and see how really quantum mechanics works in terms of mathematics, in terms of really understanding how we implement it mathematically, understand it mathematically. And we'll also start talking about the mathematical framework of which we'll use in really describing and solving problems in quantum mechanics.